All right, so good afternoon, everyone. So I am going to present to you some of the research being done in my group and with the focus on linear algebra. So I guess the first thing is, so we're going to look at ax equal b, and I guess looking at this equation, you'd think that people have solved this problem a long time ago. Probably people have been working on this for, I don't know, maybe even centuries. But I sort of want to first convince you that, in fact, it's still very much an active research area with a lot of challenging problems, and so we're developing a lot of numerical methods to address these challenges. So I guess the main take-home message is that really we're now dealing with huge data sets, and there are various reasons for these unprecedented large data sets. So first of all, new computing environment. So we're moving towards exascale computing, cloud computing, and so on. And so we can compute extremely large problems. And then we have a lot of sources of data. So obviously the web, Facebook, social networks, and so on. And then more on the hardware side, you can deploy networks, large networks of sensors that, for example, can deliver to you data every minute, and you're going to collect this data for a year, for years. So you end up with terabytes of data. And you also have lots of exciting new methods to process this data. So everybody these days seems to be working on deep learning and other statistical learning methods. And so I'll talk a little bit about that. And so as a result of these huge data sets, there is a renewed need in new numerical method. And so the key here is you want methods that scale linearly with the problem size. And so there's lots of methods out there, but actually many of them scale quadratically or cubically in the problem size. And so essentially, up to recently, they were perfectly fine. But now with these new data sets, we're hitting this bottleneck of their computational tractability. So I want to discuss, a couple of applications that my group is working on and that sort of motivate this fast linear algebra algorithm. So the first one is stochastic inversing, and so this is work with Professor Kitanidis in ICME. So we're looking at modeling the subsurface, and this has obviously a lot of applications, oil and gas exploration, CO2, and so on. And so we're using, because of lack of information, we are using probabilistic models, and we have to deal with very large dense covariance matrices. And so to give you a sense of the size, we're dealing with matrices, for example, of size 1 million. And so just the storage of such a dense matrix is really impractical. And so this is where instead of storing n squared number, you really want something that scales linearly in the problem size, so order n essentially. So another exciting area of application is optimal control. And so how can we do optimal control on a large scale? And so we're interested, for example, in applications in traffic or, again, water resource management, obviously a very important problem these days for California. And so how can we design linear methods for these applications? And so, machine learning is on the rise. And so in particular, I'm interested in techniques around kernel machines. So for example, to do a kernel support vector machine or kernel ridge regression. And these are very, very powerful methods, but very expensive. Because we're using kernel. So if you can cut down on the computational cost here, you can have both robust and very efficient methods. And so one interesting aspect of this research is you're dealing with high dimensional spaces. So previously it was sort of spatial dimension 3D, but here routinely you can have spaces of dimension 10 or 50 or even 100 or more. And so how can you design fast methods again in this high dimensional setting? And finally, of course, I have to mention partial differential equations. This is a sort of bread and butter of ICME, probably, how to deal with sparse matrices. And so, you have these new very large exascale computers. You're dealing with meshes and PDs on an unprecedented scale. And so, for example, there is a renewed need for implicit methods in solving linear systems. And so the key here is, well, we have many iterative methods, many preconditioners, but many of these methods actually fail if you keep scaling the size of the matrix. So is it possible to design methods that can guarantee a bounded number of iterations in these iterative methods for even very large matrices? So I'm just going to give you a very sort of high-level highlight of some of the methods. So, as the title of the presentation indicates, our methods rely on the so-called hierarchal matrices. And so we have actually sort of a critical mass at Stanford in this area. And so the idea of hierarchical matrices is sort of shown here. So here, this represents a dense matrix, so n square entries, and think about number of rows might be 1 million here, so you really cannot store this matrix. But it turns out it has a special structure, so-called hierarchical structure. So all the blocks in green here are actually low rank. And so the idea is you're going to decompose this matrix into essentially what is a sparse matrix or block sparse matrix, and all these red blocks are full rank, and then the rest is going to be compressed using these low rank approximations, and so you get this tiny, much smaller matrix here. But if you start with something that's size 1 million, perhaps this is still very large, and so the idea is you can recursively apply these techniques and get this hierarchical decomposition that makes sort of everything order n. And so, for example, we've designed O of n linear solvers for these dense matrices, and this is sort of the idea here. So we start from the dense matrix. We use this sort of sparse plus low rank representation, and instead of solving the original linear system, we're going to solve this larger system with a sparse matrix. So we went from dense to a sparse representation, and then we do algebra on this sparse matrix. So I'll skip some of the technical details, but there are many tricks involved here. In particular, if you want to factor this sparse matrix, you're going to get fill-in, so you're going to get dense again, and so we have to come up with some clever tricks to recompress these fill-ins and maintain the sparsity. So here are some numerical results, for example, showing you how the computational cost scales with n. So as promised, it scales linearly with n. And this is an example of the running time that we have with our fast method compared to a more classic iterative scheme. So this is for obvious applications. So our integral equations, so Stokes flow and other types of integral equations. So more recently, we've sort of tried out also mesh deformation, where also you have these dense, large dense matrices happening. So here this is showing, you start with this initial grid. You want to move this object, move the boundary. So for example, if you have a fluid structure interaction problem, this is what happens. And you want to avoid remeshing. Remeshing is very expensive. So instead what we do is we have a smooth deformation of the grid. And we can do this with these, thanks to these fast methods. So I want to finish with sparse solvers. So I did my PhD on the fast multiple method dealing with dense matrices, but I quickly realized that most of the matrices out there are sparse, so I had to convert myself to a sparse solver guy. And so it turns out that when you do sparse algebra, still you have to deal with dense matrices, so that felt more comfortable for me. So for example, if you do nested dissection, this is what your sparse matrix looks like, so you reorder it with nested dissection. And if you do an LU factorization on this matrix, you have these dense blocks that appear, and so the fast dense algebra I just showed you can be applied here. So one of my students just finished his PhD, Amir Hossein, and this is showing some of his results. So in particular, for example, here you have some classical preconditioners like incomplete LU that have difficulty converging on these problems, and with our fast solvers, we have a very fast convergence that becomes essentially independent of the matrix size or the complexity of the PDE. And so we're working on improving this. So this is so now I have 2 students working on improving these methods. In particular, the previous scheme has cost nr squared, but the rank that we need to use in our approximations is actually unbounded, so we're not truly order n. And so I promised you some order n solvers, so I need some methods that can guarantee a certain accuracy for a bounded rank, and this is what we're working on now. So these are some early results showing that for sparse matrices, we now have a general purpose black box sort of fast solver that scales linearly with the problem size, and we have very good control over the accuracy. And so finally, some results also so out of Berkeley and ICME on machine learning, and so with applications with, for example, I mentioned this kernel ridge regression, and so we're looking at using these hierarchical matrices, hierarchical format for these applications. And so the problem, as I mentioned earlier, is the fact that we're high dimensional. So we have data sets that are dimension maybe 50, 100 or more, and how can we design general purpose methods for these applications? So this is showing, for example, the relative error of our method compared to various state of the art, and so we're able to get some significant improvements on these test cases. All right, so hierarchical matrices, it's general framework for fast algebra. I like to think of it, for example, some of these methods are sort of extensions or generalization of algebraic multigrid that have been very successful in the past, and we're sort of improving even further on that. So this should be really a high impact research. So we have solvers that are order n for a broad range of PDEs and so on. And so I think one of the really important aspects of this is we're really going beyond PDEs. So I come from the realm of PDEs, but now we're looking at applications in machine learning and other essentially statistical areas like Kalman filters, optimal control, stochastic optimal control. I showed you some applications in meshing, and then perhaps this can be even extended to neural networks and many other applications. Thanks.
Well, there's certainly time for some questions.
So it's very high level, so I kept hidden all the technical details that make it work. So some of that research is shown here in the back in the posters. So actually 3 posters discuss some of this work, so you can talk to the students or. Yep.
This one is the most updated work because I used to work for a company as chief scientist for this company doing some software for IC exam.
Software for what?
Computational electrical magnetics.
Okay.
Okay, we apply H matrix, so-called H matrix, to the integral equation.
Right.
However, there's some issue if the condition number is not good. After approximation, even though we can approximate to the compress the matrix pretty well, okay, there looks very, very good. But because condition number is so bad, the final results cannot achieve the accuracy we want.
Right.
Usually 1% is good in industrial, but after compression, we always end up with like 3% or 5% error. So that's
not good enough. Okay.
Yeah. So I'm not sure if you have any comment on this.
Actually, yeah. I mean, I can definitely comment on that. I mean, so there are many people who have successfully used these hierarchical methods to electromagnetic application and so on. So, for example, I've worked with the folks in Europe and EADS and Airbus who have a very robust code there. But actually, coming back to this issue of condition number, this is sort of a very important point. I mean, and essentially, the question is, as you look at larger problems, typically the condition number worsens. Okay, and so that is the problem. The preconditioner needs to be more accurate. I mean, there's just essentially no way around that. And so, I mean, this is sort of something that I'm hoping to be able to demonstrate, in the future. But you want the accuracy of your preconditioner to increase, and so the core of the problem is what is the cost of increasing this accuracy, right? For example, if you take incomplete LU, essentially it's very costly to increase the accuracy. So you have to start ILU1, ILU2, but it's very hard to go beyond that, right? And so here, with these low-rank compression methods, you can look at the decay of the singular values. And essentially, the bottom line is it's relatively cheap to increase the accuracy. And so even if the condition number is relatively bad, you can still have a good preconditioner because essentially it's not too expensive to increase this accuracy, right? Because it's based on the decay of the singular values and so on. But obviously, if your condition number is 10 to the 20 or whatever, you have problems anyway.
We should move on because we only have the 15 minutes for talk. I'm sorry about that. I'm going to be brutal.
So I'll be here at the extravaganza
exactly.
and so on.
So after this, people will be around for the reception, and so you can ask all the questions then. Okay.
Just try to ask the question before the first beer, because afterwards, I don't know.
Thanks very much, Eric. That was great.